Hello everybody. In this lecture I'm going to go through a trend inside periodic table. What will happen with the size of element or ion when we move from left to the right side of the periodic table or down in one group? How about ionization energy when we take electron from one system? And next one, how about electron affinity? What will happen with the element when that element gets an electron? Okay. Let's start with the size of element, and we need to know this one, that when we move down in one group we are adding layers. So for example, if we start with hydrogen, this is the nucleus, and so this one is the nucleus, let's call it here proton. Then first layer for hydrogen, n equal 1, we have only one electron. So the distance between nucleus to the last layer, that is going to give us the radius for hydrogen. So this one is hydrogen. Now when I go down, I will reach lithium. Lithium, it has the nucleus, first layer, and then second layer. So now I have n equal 2, and this one is n equal to 1. Distance between nucleus to the last layer represent radius of the element. Okay. And as you go down, as you go down in one group, you are adding one layer, and because you are adding one layer, that element, it will be bigger. So we need to write this one as we go down. As we go down, a group, first we are adding layers. Okay, now, so I can say, number of layers or number of shells are going up. So I'm going to say we are adding layer to the system. New level of energy or orbit will be added. Added to the atom. Okay, so we are getting, more layers. And because we are getting more layers, size it will be bigger. Okay, size it will be bigger. So somebody can say, you forgot to talk about the protons. True that we added, layers, but also we added protons, and we know that force is equal to K, Q1, Q2 over R2 or square R. Well, Q1, let's call it electron, is the last electron, and Q2, let's call it number of protons. When we go down in one group, true, we are adding number of protons. That's true. Also, we are adding number of electrons because we want it to be neutral. But if this one goes up, if Q2 goes up, we should expect higher force. Higher force. If we have higher force, then size should be smaller. The atom should shrink. But we forgot one thing to say, that R, as we go down in one group, is increasing. So you have the right to say R for hydrogen is smaller than R for lithium. And check here. When we increase Q, exponent of Q is just 1. So if you double Q, in fact, it will be 2 times. But if you double R, if you make R 2 times bigger, when you square it, it will be 4. And we are dividing by R, because we're going to divide by R, force will be 4 times smaller than the initial. So as you see, effect of adding protons is less than effect of increasing R. And because R is getting a square, I can say the effect here is way faster. It's going to be way stronger and more effective than increasing number of protons. So as we go down, size increases. So you write this one for yourself. As you go down here, you say size. As we go down, the size increases. Okay, size increases. Now, what will happen if we move to the right side of the periodic table? Let's say we are moving in one group. Okay. Here, this one you have it from your slide. Sorry, I meant the period. I meant one period, not a group. But the last stuff that I mentioned, as we go down, we are increasing layers, and because we are increasing layers, atoms is getting bigger. Okay. Because n is going up. Next, when we move in a period, we're not changing n. N is equal to 3, and here still is 3. So we're talking about identical n. The only difference is going to be here, number of protons. This one starts with 11 protons. Well, this one is 12, 13, 14, 15, 16, 17, and 18 protons. So number of protons are going up. How about number of electrons? Yes, number of electrons are also going up. So you might say, okay, I added the protons, but also I added electrons. And I know electrons are going to build repulsion. So I should not, expect any change. And I'm going to show you why it's not correct to say it. Okay, let's choose two elements. We go with, for example, sodium, and next one we can go with phosphorus. So sodium 11. Right, let's write the electron configuration. It will be 1s2, 2s2, 2p6, 3s1. Let's show the layer. First layer, it has 2 electrons. Second layer, it has 2 plus 6, 8 electrons. And the third layer, it has only 1 electron. And here is the nucleus of sodium. It has the protons. Distance between last electron or last shell to the nucleus represents size radius of the element. So this is R for sodium. Okay. How many valence electrons do we have? Valence electrons equal to group, it will be just 1. Because the highest n is equal to 3 and represent the period. And we have only one orbital that comes with n equal 3. So we said, let's count number of electrons in it. It's just 1. Okay. How about core electrons? Core electrons, you covered the last layer, whatever left, 2 plus 8, 10 core electrons. Okay. We have 10 inner electrons. Okay. 10 inner electrons or shielding electrons. And remember, effective nuclear charge is going to be equal to number of protons minus S. And S is talking about core electrons. So in this case, for sodium is going to be 11 minus core electrons. We have 10. It's just a plus 1. Okay, just a plus 1. How about we said phosphorus? Phosphorus is 15. So it will be 1s2, 2s2, 2p6, 3s2, and 3p3. So first layer, n equal 1. We have 2 electrons, n equal 2. We have 2 plus 6, and n equal 3. We have 2 plus 3, 5 valence electrons. Okay. And here is our nucleus. This is This is R for phosphorus. Now, see which one is bigger, sodium or phosphorus. When I look to number of core electrons, I see 2, 2, 8, 8. So that's not the issue here, it looks. And how about the last layer? We have 1 electron. We have 5 electrons here. Okay. And check the nucleus. Nucleus, you have 11 protons versus 15 protons. For sodium, I said I have 11 protons and 1 and 2 and 3. You have 2, 8, or 2 plus 6, and just 1. For phosphorus, have n equal 1, 2, n equal 2, 2 plus 6, and n equal 3. We have 2 plus 3, 5. So for phosphorus, you go with highest n equal 3, so the period is equal 3. Valence electrons equal to group equal to 2 plus 3, 5. And core electron, we have 10. So how about the effective nuclear charge? It will be Z minus S. So it will be 15 minus core electrons. We have only 10 as a plus 5. Plus 5. Well, sodium, it was, so if I say this one for phosphorus, for effective nuclear charge for sodium, we said 11 minus 10 core electrons plus 1. So the difference here, is going to be number of protons. The one that has more proton is going to apply higher force. Because it's applying higher force, it will apply higher attraction force. That means it will be smaller. Phosphorus, it will be smaller than sodium because it has more effective nuclear charge than sodium. So in one n, identical n, when we are sharing n, like n equal 3 or n equal 3, sodium versus phosphorus, n equal 3, n equal 3. We cannot judge based on n. Okay, we cannot judge based on n. So in this case, I need to look to number of protons. Protons, I have 11 protons versus here I have 15 protons. Which one is going to apply higher force? The one that has more protons. So that means size of phosphorus, I don't know why I keep adding positive charge. Size of phosphorus is going to be smaller than size of sodium. So to the right side of the periodic table, because we are increasing number of protons, size decreases. Down in one group, size increases. Okay, so that's the reason when we move in one period, because effective nuclear charge is going up and we are adding the electrons, we are adding the new electrons to last layer. We're not adding any shielding effect, new shielding effect. Size is going to be smaller. Okay, size is going to be smaller. Okay. So now let's review whatever we said till now. We have a group versus period. Okay. In the group, n is not identical. N is not identical when we are talking about group. So, okay, I'm going to put a star on this one. And from now, when I compare two elements, I'm going to go with N. The one that has a smaller N will be a smaller element. So, for example, calcium versus, let's say, element like lithium, I will assign N for them, and I will judge based on N. What's the N for calcium? Calcium belongs to N equal 4, and lithium N equal to 2. You want to order them based on size. You go with N. The one that has smaller N, it will be smaller. So I go, lithium is going to be smaller than calcium. When we are talking about period, N is identical. Identical. So then I'm going to say, look for number of protons. Look to number of protons. For example, we go with silicon versus, say, silicon versus which element? Chlorine. Silicon times number 14, chlorine 17. Silicon belongs to N equal 3. Chlorine N equal 3. So I cannot judge based on N. Next, I get number of protons. Protons equal to 14. This one equal to 17. If they are sharing same N, then go with protons. The one that has more protons, it will apply higher force and it will be smaller. So in this case, I'm going to say protons equal 17. Okay. This one, it will be smaller than the one that it has less protons. So you go with chlorine, it will be smaller than silicon. Okay. So if you are talking about a group, when you go down in one group, you're not going to have identical N. N is increases. And because N increases, judging it will be really easy. You go with the smallest N. The smallest N is going to be the smallest element or the smallest size. When you're talking about one period, N is identical. When you move from left to the right side of periodic table, you are not changing the shielding electrons. Okay. You're not changing shielding electrons here. From sodium to phosphorus, I did not change shielding electron or core electrons. They are the same. And outer electrons are not going to affect shielding effect. Outer electrons, they do have shielding effect, but it's really small. So if you want to judge, you go with protons. Because we have same shielding effect, only effect that is left is going to be the traction force from nucleus. 11 protons versus 15. The one that has more protons, it will apply higher force. So it will be smaller. Silicon versus a chlorine. Silicon, it has only 14 proton, chlorine 17. So chlorine, it will apply higher force, and the chlorine, it will be smaller than silicon. Okay. So till now, I was talking about neutral element. Okay, neutral element. What will happen if we switch to ions? Okay. But before I jump to ions, I'm going to show you a trend. Inside the periodic table when it comes to size. Okay. Here. So we start with hydrogen. hydrogen belongs to n equal 1. That means hydrogen should have the smallest size. Smallest size, like, at least in this case. But if you have helium, if you put helium somewhere, helium, it will be the smallest technically. So if I put helium here, let's say helium, that's going to be the size. Okay. From hydrogen to helium, from left side of the periodic table, we are moving to the right side. N equal 1, n equal 1, number of protons 1, protons equal to 2. So helium, it will be smaller. Okay. After helium, the next element is going to be lithium. But lithium, it has one layer more. So size, it will be bigger. You will see a jump. And then from lithium to neon. So here, lithium to neon. We are moving to the left side, the right side of the periodic table. N equal 2, n equal to 2. Number of protons equal to 3. Number of protons equal to 10. As we move to the right side of the periodic table, because we are in increasing number of protons, and still we're talking about same n, or identical n, size should get smaller. And it does. Okay, until we reach neon. Okay. Now, after neon, next element will be sodium. So now we are adding new layer, and you will see another jump. Okay. Same trend. You go with sodium this time to argon. N equal 3, n equal 3. Number of protons 11, protons 18. So again, size will be smaller. And we reach to N4, now there is a jump. Okay. From N3 to N4, there will be a jump. You see same trend till you reach this area. It's almost flat. Okay. Almost flat. This is a transition metal area. That means you're talking about d orbital. Okay, we have d orbital as the last orbital, and you see same thing here. Again, this one is a flat, and this one is belong to transition metal area or d orbital. Okay, before we talk about the transition metal area, let's check the minimum and maximum points. Minimum size or radius belong to group 18 or noble gases: helium, neon, argon, krypton, and then xenon. So the smallest size in one period belong to noble gases. The biggest size in one period belong to group 1: hydrogen, lithium, sodium, potassium, and rubidium. All of them belong to group 1. Group 1 here, group 1, and group 1. Well, here group 8. So first element from any period has the biggest size. Last element from that period has the smallest size. Okay, let's talk about transition metal area and pick 2 elements. I go with, let's talk about which element let's choose. I want to be careful about the elements that I'm picking. So I go with this element, scandium. Then I go with, let's say, vanadium. And then go with iron. And then let's go with nickel. write the electron configuration for this element. Electron configuration, it will be 1s2, 2s2, 1s2, 2s2, 2p6. So 1s2, 2s2, 2p6, 3s2, 3p6. This is equal to 18 electron, and you can show it by argon. And then here, 4s2, 3d1. So I can write it as, okay, I can say scandium is equal to argon, 4s2, 3d1. Here it will be argon, 4s2, 3d2. Argon, 4s2, 3d. Sorry, this one is a 3 actually, because it's a 23. (3d6), and here argon, 4s2, 3d8. I want you to be sensitive to the last electron. Last electron is going to the d orbital. D orbital. And check the number that's written in front of the d orbital. That number is a 3, not 4. Okay. So last electron is going to d orbital. And that d orbital is belong to the third layer. And what's the last layer? The most, outer, like the outer layer is the 4, and is like we showed by 4s orbital. Okay, so here I go with scandium. We have N1, 2 electrons, N2, we have 2 plus N3 and N4. N4 we have only 1 orbital, that it has 2 electrons. It's a 4s with 2 electrons. But the third layer we have 3s, 3p, and 3d. So we go 3s with 2 electrons plus 3p, 6 with 6 electrons, and the 3d with 1 electron. 1 electron. Okay. So we added the electron to inner layer, not outer layer. Okay, and this is the one that we need to be sensitive about it. So the highest n, which is equal to the period, is equal to 4. You want to measure the size, you go with from the nucleus to last here, this electron, or last layer. And I added the electron to inner layer. Okay. When I go to, let's say, from this element that I picked, I keep adding electron, but the electron is going to the d orbital. When I go to vanadium with the 23 electrons, it will be N1, 2 electrons, and 2 plus 6, and 3, 2 plus 6 plus 3d, 3. So we get 3 electrons. And N4, we have 4s with 2 electrons. Again, from nucleus, last layer. Now, let's compare these two and see which one is going to be smaller, this or that one. Okay. And when I look to number of layers, we're sharing, n is equal 4, so identical n. Because it's identical n, we can't say anything. We are moving from the left side of the periodic table to the right side. So we have to talk about number of protons. 21 protons versus 23. The one that has more protons should be smaller. But the graph I showed you, they are, like the change is not a dramatical. Change was not really dramatical one. And I said, like, we need to talk about it. Let me find the graph. Where I put the graph. Okay, here. Change is not dramatical. It's almost flat. Yes, it's going down, but it's not like those. It's not steep or sharp. Okay. We are adding a proton. When we move from scandium to vanadium, we are adding protons. We added 2 protons, so size should be smaller because we are adding protons. But check the electron, the last electron that you added. You added electrons to inner layer. Okay. Inner layer, not outer layer. And inner layers, these 3 layers, they will apply shielding effect. Okay. They will apply shielding effect. You can call them, core electrons. And more inner electrons or core electrons you have, the higher shielding effect you will see. And shielding effect, it will, it will cancel the positive charge or the attraction force to some extent. So you say effective nuclear charge equal to Z minus S. Because we are adding electrons, last electron, to inner layer, not outer layer, shielding effect, or S, is going up. And we are subtracting S from Z, which is number of protons. So as you see, we have 2 factors that work against each other. Decreasing a proton, number of protons, it will make the size smaller. So as number of protons goes up, size decreases. But when we increase core electrons or inner electrons, when inner or core electrons decrease, then size is gonna go up. Okay. Which one is more effective? It's hard to say it. Okay. And they are almost close to each other. Their effect almost close to each other. That's the reason, you don't see huge change. Okay. Like here, 4s1, 4s2, this is 3d, okay, 3d1, 3d2, 3d3. And as you see, by increasing the number of electrons inside D, is getting almost flat. Okay. At the beginning, when you added 1 electron here, it's just 1 electron, and the change is not dramatical. We say, effect of protons, it will be more important than adding electron to the last layer, adding electron to the inner layer. But as you increase number of electrons here, as this one goes up, then these two start to work completely against each other, or be equal. They are against each other, but they will be equal. Now that they will equal, they will cancel each other. So for example, from vanadium to iron, d orbital in this case, it has 3 electrons. This one, it has 6 electrons. We added, like we built good number of electrons inside the d orbital. Now they will have repulsion between them. And if you have more repulsion, and then size is going to be slowly getting, bigger. And so from vanadium, which is this one, vanadium is here, V1, 2, 3, D3. When we move to iron, iron is going to be this one, iron. You see here, it's almost flat. Okay, almost flat. But after that one is gonna go up because you are gonna build really huge repulsion, and that repulsion cannot be canceled by effect of having more protons. For nickel, we have almost, like we have 3 of this orbital full and 2 half occupied. So I'm going to say the repulsion is going to be huge. Because repulsion is more, then you should expect increases with the size when you move from iron to nickel. And from iron to nickel, just going to be this element. Now, slowly we're going to build some, like a repulsion, and size it slowly is going to go up. Okay. It's really hard to say it. It's hard to, like, you say, oh, okay, is it going down or up? You can say it's almost flat. Say almost flat for this one. But when you go with, for example, copper here, copper still is copper belongs to N equal 4, but copper is bigger than iron because copper has D10, and D10 is going to have too much repulsion. Okay, so when we are talking about transition metal, we have 2 effects. First, when we move from left to right side of periodic table, we are increasing number of protons. As number of protons goes up, size decreases. That's a good one. But when we move to the right side, we are adding electron to the d orbital that belong to inner layer. Okay, inner layer, N equal 3. And if we increase number of inner electrons, that means we are increasing shielding effect. Because we have more shielding effect, size will go up. Okay, which one is more important? Number of protons or number of core electrons or shielding effect? It's really hard to say it. You need to measure it, the element, like you have to use some technique and measure it, and then you can judge about it. So when it comes to transition metal, you have the right to say they are almost same. They are almost same because you have 2 effects that they are against each other. Okay. So now I'm going to switch to iron, and I want to talk about their size. So we said when we are talking about neutral element, the trend for size to the right side of the periodic table decreases, down in one group and increases. When you have ionic compound, we have a cation or anion, the trend is going to be the same. To the right side of periodic table decreases, down, and increases. How about 9? It will be the same. Okay, so 9, it will be the same. So I should say either 9 or cation. So the best thing is to say here, let's call it, ionic. Ionic, okay. Ionic radius or radii. It can include, like both cation and anion. To the right side decreases, down and increases. Okay, so for neutral, we said Mg versus barium. This is here belong to N equal to 2. Sorry, N equal 3. I believe this one is N equal 5, I believe. Let me check the periodic table. Barium N equals 6. Well, 6. As we go down one group, size increases. So barium that's bigger size than Mg. And here we said we go with number of protons. An example, nitrogen versus fluorine. Nitrogen n equal 3, n equal 2. Fluorine n equal 2. Number of protons. Here we have 7. This one 9. The one that has more protons, it will be smaller because we are talking about identical n. So size of fluorine, it will be less than nitrogen. Now let's talk about their ions and see what's the trend for them. Okay, I go with nitrogen minus example 1 versus fluorine minus 1. And I want to compare their sizes. Okay. If you give it 1 electron, it will be this one, it will be here for n minus 1. It's going to be 1s2, 2s2, 2p4. So the highest n is going to be 2. Number of protons equal to 7. Number of electrons equal to 8. For F minus 1, you go 1s2, 2s2, 2p8. Sorry, 6, my bad. N equal 2. Number of protons equal to, this one it will be 9. Electron, okay, total electron, we have 10. Okay. If you are sharing N, you judge based on number of protons. Okay. You're sharing N, you judge based on number of protons. One that has a small number, one that it has more protons, it will be smaller. Okay. So in this case, because both of them are belong to n equal 3, I'm going to say size of fluoride, it will be smaller than nitride. Okay. So n minus 1 is bigger than F minus 1. Okay. How about this? N minus 1 versus n minus 3. Okay. N minus 1 belong to n equal 2. This one still is n equal 2. N minus 1, we said 1s2, 2s2, 2p, 3 plus 1, 4. So the highest, okay, highest n equal 2, period is equal to, group or valence electrons equal to 4 plus 2, 6. Core electrons equal to 2. Okay. How about total electrons? We have 7. So here, 7 plus 1, 8. Compare it with N3 minus. It will be 1s2, 2s2, 2p, 3 plus 3, 6. N equal 2, period is equal to, group or valence electrons, it will be 2 plus 6, 8. Core electrons equals 2. Total electrons equal to, we have 10 electrons. I think I made a mistake. Yeah, no, that one is 8, correct. Okay, this one is 10. Okay, so now I want to judge and see which one is bigger. Check n. N equal 2, n equal 2. We are sharing n. Because we are sharing n, we have to look number of protons. We have, how many protons we have? We're talking about potassium, sodium, nitrogen. 7, 7. So we can't say anything based on number of protons. How about core electrons? Core 2, 2. Difference is going to be here. Check total electrons. You have 8 versus 10. This one, it has more electron. Because it has more electron, it's still the same number of protons. I will say the repulsion is going to be so high that the system has to let the size increases, otherwise it will collapse. Every time you are adding electron to the system, that electron comes with negative charge. It will build repulsion. Okay, it will build repulsion. So N3 minus is going to be bigger than N minus 1. For sodium, for nitrogen, we said this is the nucleus with 7 protons, N1, N2. N1 is going to be S1, S2. Here, 2 electrons. Then we have 2s2. Then we will have 2p3. Versus, this is nitrogen, n minus 1. Okay. You have a nucleus, still 7 protons. N1, you have 2 electrons in it. 1s2. Then we'll have 1s1, 2s2, 2p4. We are adding 1 electron to it. So I go here, same electrons. I will add electron. I have 1 here and 1 there. These 2 electrons will hate each other because they are carrying same charges. They will have repulsion. Because they will have repulsion, they will push each other. They try to be way far from each other. How can we keep them in that area without letting the system to collapse? Only way to do it is let the size increases. When the size increases, the distance between these two will be bigger. Okay. If you increase this one, okay. So let's assume this one increases to here. Okay. So assume this is still is n equal to 2. Then the gap between these 2 electrons, it will be bigger. Because the gap is bigger, force it will be less. And force is equal to K, Q1, Q2, divided by R2, the square of R. If this distance gets bigger, and force it will be smaller. And the force here in this case is repulsion between the 2 electrons. So as we increase number of electrons, repulsion is going to go higher. That means size it will be bigger. So when you're talking about anions, you need to be careful about the charge. So here, phosphorus -1, phosphorus -2, phosphorus -3. We're talking about phosphorus. So it's same N, same number of protons. 15 protons. All belong to N equal 3. Difference is going to be here. 15 plus 1, 16 electrons. This one is 17 electrons. And here, 18 electrons. And protons still 15, 15, 15. As you see, as we increase number of negative, the negative charge, we will have bigger gap between the protons and electrons, total electrons. Because we cannot apply higher force on those electrons, they can go a bit further from the nucleus. So size is gonna get bigger. Okay. How about cations? Okay. Cations trend will be opposite this time. For anions, we said neutral element. This is a phosphorus neutral element. It will have the smallest size, and anions always will be bigger than the mother element. So the neutral element, like chlorine, it will have a smaller size than the anion. When it comes to cation, for cation, the trend is different. Cation, let's say we're talking about sodium. 11 protons. 1s, 2 here, 2 electrons. 2s, 2 electrons. Then we will have 2p, 3, 2p6. And this one is the 3s with 1 electron. Distance between nucleus, the last layer, represent size of the radius of the element. I have 11 protons and 11 electrons. I add them to be neutral. Now take 1 electron from this element. When you take 1 electron, you take it from the last layer. So you target this electron. Remember, sodium and 1, 2 electrons, and 2 plus 6, 8 electrons, and n equal 3. We have just 3s with 1 electron. So we're targeting that electron. If we want to take electron from the system, we're going to take it from here, last layer, because this one is far from nucleus. It costs less energy to take it. If you take this electron, then this one is going to be the outer shell. And number of core electrons will be different this time. So let's take 1 electron from it. You go with sodium and 1, 2 electrons, and 2 plus 6, 8, and 3, just 1. Core electrons, those are the core electrons. This one is the valence electrons. You take the valence electrons, compare it with sodium plus 1. You will have N1 with 2 electrons, and N2, 2 plus 6, 8 electrons. This one is gone. It's gone. So now let's check the core electrons. Core electron, only 2. That one, it will be the valence electrons. Check the size from nucleus to the last layer. So you have the right to say sodium has bigger size than the cation. Cation of any element is going to have a smaller size than the neutral element. This is opposite of the anions. Anions, we said chloride, it has smaller size. My bad, this one should opposite. I'm sorry about it. Go this way. Chloride, it has smaller size than the chloride. They are opposite. Neutral element, it has bigger size than the cation. So any neutral element is going to have bigger size than cations of that element. When it comes to anions, we say neutral element of any element is going to have the smallest size between neutral and the anions of that element. Okay, so the trend is opposite between cations and anions. Cations will be smaller than the neutral, and anions will be bigger than the neutral. Okay. So for anions, you go with N. It has the smallest size, then N-1, N-2, N-3. But when it comes to cations, you go, for example, S+4, it will have smaller size than S+3, S+2, S+1, and S0. Check the neutral element. For anions, neutral element has the smallest. For cations, neutral element has the biggest size. And I'm going to start the lecture here. Thank you, guys.